Yes, the recording should have started. Okay, welcome everyone. So today is the first seminar talk this semester for the UCF Computer Architecture seminar series. And today we're gonna have Preyesh Dalmia from NVIDIA to give us talk on GPU synchronization and communication overhead. So Preyesh is a deep learning architect at NVIDIA, where he works on enhancing deep learning model training performance by working on optimizations throughout the software and hardware stack. He recently graduated as a doctorate in computer engineering from the University of Wisconsin-Madison, where his research focused on data movement in heterogeneous systems. During his doctorate, he proposed optimizations to mitigate synchronization and communication overheads in GPUs at different scale from both a software and hardware aspect. And Preyesh, the mic is yours.
All right. Hi, everyone. It's great to be here. Thanks, Dee, for inviting me for this talk. Today I'm gonna talk to you about my work that I did during my PhD on reducing synchronization and communication overheads. So just to give an outline to everybody, I'm gonna briefly go over what are the challenges that come about for synchronization and communication, and then move over to briefly give you an idea of what work we did. I won't go into detail because the talk is limited to 45 minutes. I will give D the papers, which will explain the work in more detail if anybody is interested. And I would like to go over my recent paper, which recently came out at Micro, in more detail than some works that I did previously. Cool. So let's start by understanding why we need to reduce synchronization and communication overheads in GPUs. Traditionally, general purpose programmable accelerators such as GPUs were used for applications related to graphic or scientific computation. These applications primarily exhibit streaming data access patterns, as we are aware in GPUs traditionally. They had little data reuse and relatively infrequent synchronization because it was expensive when needed. However, GPUs have now evolved from primarily being used in data parallel streaming applications to now finding use in modern applications that challenge traditional semantics associated with GPUs. In general, these applications shown here have different access patterns and synchronized simulations, which involves varying amount of data sharing, reuse, and fine-grained synchronization. Let's see some of the applications that are run on the GPUs which rely on frequent synchronizations. Applications such as shortest path search here or persistent RNNs proposed back in 2016 require device-wide synchronization in form of global barriers for these applications to function correctly. Applications such as machine learning and graph analytics need some synchronization to avoid data races to shared variables. These applications rely in most cases on read, modify, write atomic updates to shared global memory to accomplish this synchronization. Prior work has shown that even simple forms of synchronization can enable programmers to design GPU solutions with better utilization and synchronization-free algorithms, motivating application developers to pivot towards synchronization-heavy implementation. Thus, synchronization is a key component for many modern applications, and there is a need to efficiently support it. Before I get into the details of the work, I would briefly go over the background information relevant to the talk. Just like a brief GPU 101, GPU program consists of multiple kernels of thousands of threads. The thread hierarchy is shown in the figure on the right. As described earlier, a group of thread blocks are used to execute a kernel. Figure on the left gives a simplified view of the GPU architecture. It consists of streaming multiprocessors or CUs with their own L1 data caches and shared memory. The whole device has a common L2 and main memory, as L2 forms the last level cache and is first common shared point across all streaming multiprocessors. All device scoped accesses are done at the L2. So just for reference for anybody who doesn't know scope, so a scope is defined as what is the level of the memory access after which it is consistent. So a device level access should be consistent across the whole device. GPUs traditionally use simple software-driven valid-invalid style coherence protocol without need for ownership request, write-initiated invalidations, Snoopy buses or directories, which you might have read in a CPU microarchitecture course. These protocols worked well till the time workloads only relied rarely on synchronization, as synchronization is very expensive with these protocols when required. To mitigate these high synchronization costs, scoped memory models were introduced. They allowed programmers to limit the visibility required by a synchronization operation. However, when the synchronized operation is globally scoped, synchronization can still be very expensive, as unlike CPUs, where you could potentially obtain necessary permissions to do atomic operations locally, GPUs piggyback on atomics being global memory operations going out to the last level cache to avoid adding complexity to the coherence protocol. The rest of the talk, I will be discussing the solutions to all the three types of global synchronization that we have proposed solutions for. But before that, first, let's talk about a high-level overview of what the different challenges with global synchronization are. Okay, so how does synchronization show up in GPU applications? Here in this figure, we show a basic GPU execution model where a grid of thread blocks are executing a kernel. A thread block is formed from multiple warps, and a warp is formed from multiple threads, 32 or 64, depending on the manufacturer. Synchronization is used in different ways. Synchronization is required to manage race conditions for shared object updates. They can come in form of shared memory atomics if the threads sharing the variable are from the same thread block. Otherwise, global memory atomics are used to achieve the synchronization. These atomics can be relaxed. That is, they don't require any ordering with other memory requests. However, these are still very expensive as they have to go all the way out to the last level cache, which can quickly become a bottleneck. Data sharing can also be achieved using locks and semaphores, where data loads and stores are bounded into a critical section. Another use of synchronization is to ensure two threads that have reached a common point in the program execution are moved together after that. If the two threads are within the same block, sync threads directive is used, and if they are in different blocks, then we have to use a global barrier represented here by global sync. Synchronization is also used in an implicit manner where synchronization due to release acquire directives ensure that private caches for the processors are maintained in a coherent state. Using these animations, I will be showing you how the synchronization types we discussed previously manifests in a GPU system. And then subsequent slides will explain what performance gaps are in their current implementations. This figure represents a monolithic GPU system with streaming multiprocessors having their own private L1 cache / scratchpad memory with a shared L2 across all processors. So as you see here, updating variables shared across threads from different thread blocks requires device scoped atomics to the LLC, which are expensive since L2 accesses in modern GPUs can take over 100 cycles. Next, instead of relying on relaxed atomics, let's say the program relies on regular data loads and stores, which are bound inside a critical section using a lock. So now all the threads try to acquire the lock. This primitive scales badly due to contention for said lock. Next, we have implicit sync at kernel boundaries. Private caches in GPU need to be kept coherent. This was limited to L1 caches in monolithic GPUs, but then we moved to multi-chiplet GPUs, and now L2 caches have also become private to a subset of the processors and require the same sync maintenance ops, which are acquires and releases, as you might be familiar for L1 caches. Now we have to do the same thing for L2 caches. Now, having looked at how different forms of synchronizations are implemented, I will now discuss the challenges associated with them and also what are our solutions to those challenges. We first target the bottlenecks in explicit global synchronization resulting from use of relaxed atomics for shared memory updates. The challenge here is that atomics in GPUs are not implemented efficiently. They have to go all the way out to the last level cache. Standard atomic latency is high, and high percentage of atomics in an application can quickly make them a bottleneck. Our insight here is that graph analytics and machine learning applications use commutative relaxed atomics, where the order of the update does not matter and the value is not read before the end of the kernel. We propose to cache these updates locally in a per SM buffer in an attempt to reduce the bottleneck we just discussed. Sometimes programmers can use relaxed atomics, or instead they could choose to use software synchronization through designated synchronization variables. Think of locks, semaphores that you might have read about in your OS course. The challenge here is that existing GPU synchronization primitives either scale poorly or suffer from live lock or deadlock issues due to heavy contention between the threads accessing these variables. Our insight here is that redesigning these primitives to better fit GPU's unique model and memory hierarchy is necessary for better for better performance. Hence, we propose multi-level sense reversing barriers and priority mechanism for semaphores that can be designed within the GPU architecture with keeping the GPU architecture in mind to improve the performance and scalability. In the previous few slides, we have seen problems with explicit fine-grained synchronization using software primitives. However, as GPUs continue to evolve, even implicit global synchronization, which happens at kernel boundaries, can hurt application performance. The challenge here arises from a recent pivot by GPU vendors towards chiplet-based designs, where the shared memory boundary has moved from L2 cache to the L3 cache or global memory. This necessitates a need for bulk cache validations / write back of the L2 cache in these chiplets, leading to more expensive interkernel reuse. Prior work and we have observed that most applications in GPUs have kernels that have reuse across kernels, either through two kernels reading the same data or from a producer-consumer access pattern. This can be leveraged to reduce the implicit sync cache maintenance operation till the time functional correctness is maintained, thereby improving performance. We propose a producer-consumer dependency tracking mechanism called CP-elide that applies an intelligent acquire-release technique to promote inter-kernel reuse from within the L2 cache and improve performance. To summarize, the three inefficiencies we target are: first, bottlenecks due to use of device-scoped atomics to update global shared variables; scalability issues with GPU software synchronization primitives; and implicit sync causing loss of inter-kernel reuse from L2 caches that have now become private after move to chiplet-based designs. We propose hardware-software frameworks that use knowledge of the GPU memory hierarchy and algorithmic properties of applications to improve the efficiency of GPU global synchronization and advance the state of art for global synchronization in GPUs, resulting in performance and energy improvements across a plethora of GPU applications. Next, we will be going through a brief summary of our work which deals with global synchronization using device scoped atomics. Uh, the paper was called Only Buffer When You Need to, reducing on-chip GPU traffic with reconfigurable local atomic buffers. As alluded to earlier, modern applications use read, modify, write memory transactions to ensure correctness. For example, in machine learning training, many accesses uh, are regular loads and stores. However, ML training algos use um, stochastic gradient descent during backprop, which requires performing atomics to update the shared weights. These shared weight updates are a big source of inefficiency in ML training. In graph analytics, as for an input graph, multiple vertices may be connected to each other. Atomics must be used for the updates to avoid data races. This is a problem because atomic transactions can go all the way out to the LLC and can increase the serialization bottleneck. Our analogy is to think of them like slow, extremely slow turtles because of them being relatively time expensive operations. Thus, we propose to improve the efficiency of these atomics or slow turtles by exploiting the commutative nature of atomics in these applications. Combined with the fact that these updated shared variables are not read before the end of the kernel, we can cache these atomics locally in a per core small buffer. These buffer extend the dynamic partitioning feature already present in the local SRAM block, which is basically they divide the L1 cache and shared memory from a big SRAM block inside the GPU, such that we don't waste crucial SRAM space in case there are no commutative atomics in an application. We saw a benefit in terms of performance, energy, and reduction in interconnect traffic across the micro benchmarks and the benchmarks that we evaluated for this work. With our proposed mechanism, slow turtles going out to the LLC reduce, and even the turtles which do end up going have to have less traffic to contend with. Next, we will talk about our work on GPU synchronization primitives. The paper was titled Improving the Scalability of GPU Synchronization Primitives. As I alluded to earlier, next generation GPU applications repeatedly access shared data in global memory across threads from different thread blocks. As we saw with the LAB work, sometimes programmers rely on relaxed atomics to enable this. But in some cases, that is either not possible or it is more efficient to use device-wide synchronization primitives such as mutex, locks, semaphores, and global barriers to ensure correctness and have regular loads stores to shared variables inside critical sections. However, GPUs typically run kernels with millions or billions of threads. Thus, synchronization variables are heavily contended, even after common optimizations such as using just one master thread per thread block to perform the synchronization. Accordingly, it is important to improve support for explicit global synchronization using software primitives, especially at high contention levels. Our insight for this work is that synchronization primitives should be designed with the GPU's parallelism, memory hierarchy, and consistency models in mind. Using this insight, we propose a multi-level sense reversing barrier called GSRB, in which most threads use cheap, locally scoped atomics, reducing global atomics. They provide less contention for global synchronization variables, which is, in this case, the counter for the global barrier. Across three modern GPUs, GSRB improves performance by 34% over CUDA cooperative groups, which is the state-of-the-art barrier mechanism used inside NVIDIA GPUs for 5 full-sized benchmarks at various contention levels. We also propose a priority mechanism for GPU semaphores, which reduces the time spent on synchronization while using the primitive. Across three modern GPUs, we see 83% better performance than the state-of-the-art implementation from academia which is from the heterosync suite. An important aspect that we found in heterosync implementation that for at larger scales, the semaphore started to live lock. Our design eliminates live lock as compared to heterosync, which is a big win because we are continuing to scale the amount of GPUs we use for a modern application. Next, I'm going to talk about my work to reduce synchronization at implicit kernel boundaries. This work was recently presented at Micro 2024, and the work is titled CP-Elide Efficient Multi-Chiplet GPU Coherence. So demand for GPU computing for some applications has outgrown what a single die can deliver, and hence GPU manufacturers are now turning to new packaging technologies such as multi-chip, multi-GPU modules. With an additional level of memory hierarchy, new challenges for GPU memory models and coherence protocols have come about. The one we deal with in this work is L2 caches, rather than being shared across all processors, now become private to a subset of the processors and are hence subject to implicit synchronization that happens at kernel boundaries. So why do we care about L2 caches becoming private? Now that the L2 caches are private to chiplets, lines in the cache are either invalidated or written back to main memory at a kernel boundary. This always used to happen for L1 caches, but is now extended to L2 caches. This means all the data that one could have reused from the L2 caches is now lost. Modern GPU applications frequently rely on reuse from read-only data or producer-consumer form of sharing. This inherently has a huge performance impact, as you'll see on the next slide. NVIDIA research came out with HMG in 2020, where they analyzed common GPU workloads in multi-GPU, multi-chiplet setting with bulk invalidation of L2 caches. They found to have 29% performance difference with respect to idle caching, that is no cache coherence, which is not actually far from what GPUs typically follow for monolithic GPUs. Additionally, previous work called LADM, while comparing different designs for thread block management for multi-GPU designs, came to the conclusion that no matter what thread block management scheme they used, there was still an 18% performance gap to a monolithic GPU of the same size. Because you guessed it right, loss of interkernel locality from within the L2 cache. Carve also had a similar observation for a bunch of HPC and machine learning applications, where they showed loss of interkernel reuse hurt performance by 45% across applications in a NUMA GPU system. So this is an important problem to solve for chiplet-based designs. Our key insight into this problem is that GPU kernels generally have some read-only data, and in other cases, kernels share a producer-consumer style dependence. If we are able to track this dependence, we could potentially avoid unnecessary acquires and releases. This tracking mechanism would need runtime scheduling information. The only place where this is readily available is the GPU's interface connecting to the host software, called the GPU command processor. The CP also has access to the kernel packet, which we will be adding information such as access mode and ranges as part of this proposal. Thus, we propose CP-Elide, which houses a dependency tracking table inside the CP that keeps track of all data accessed by the program on every chiplet. Our solution sees performance gains over the baseline chiplet architecture and state-of-the-art techniques such as HMG. Also, with the ever-changing application space, there might be a change in requirements for the CP-Elide table. Well, the CP-Elide has that covered too, because it is a reprogrammable structure, as it is a part of the CP. Now let's take a deeper dive on chiplet GPU architecture we saw earlier. Chiplet-based GPUs introduce an additional level to the memory hierarchy in form of L3 cache. Each chiplet contains multiple L2 cache banks that are coherent within a single chiplet, but in some designs, incoherent with the rest of the system. Remote access either goes through an inter-chiplet link or through memory with a preceding write-back request. The diagram I showed you on the previous slide was a simplified version of the multi-chiplet arc. This is closer to what a real system looks like, where the HBM sites are divided across the chiplets, creating a NUMA memory access paradigm. Now let's have a look at the CP and understand why it's critical to our proposal. The CP has many responsibilities, such as initializing extra metadata from the app binary and initializing the register file, amongst other things. However, the two things CP does, which is important to this work, is that CP processes the kernel packet that the driver sends it and is also responsible for portioning the work across the CUs based on the kernel grid dimensions. CP having access to dynamic scheduling data structure base addresses info, that makes it the perfect place to house CPLite because it needs that information for its operation. Our first design proposal is to split the command processor into two parts. This design decision stems from the fact because there are basically two levels of choices involved here. The first choice is to decide what chiplets do you want to run on, and then what CUs on those chiplets do you want to run on. Thus, rather than having one big CPU which decides everything, this breakdown of CP into an hierarchical structure allows for greater scalability. Thus, in the new structure, it makes sense to place CPLite inside global CP, as it only needs to know what chiplets are going to run on a given kernel, in a given kernel. Zooming in a level, this is how the proposed CP block looks like. To your right, you will see our newly added CPLite table placed inside the memory. And along with it, CP inside control logic that reads the CPLite table and decides the need for future acquires and releases. Now let's open the lid further and take a look at the CPLite table and structure in more detail. The CPLite table is updated after each kernel launch, where a new entry is created for each data structure that is accessed in the kernel. It maintains a chiplet vector that has 2 bits per chiplet, 2 bits because the data structure can be in 4 states, which are described in the next slide. Information is retrieved from the kernel packet about the different data structures accessed and what modes they are accessed in. We then combine this information with information about scheduling of the kernel to generate the chiplet vector. I am going to give a detailed example of how this is done later. So what are the states that CPLite designates data structures with? The 4 states that a chiplet can have a data structure in according to CPLite are not present, dirty, stale, and valid. Dirty and valid follow traditional definitions as you would be used to. Stale state is when the data structure is in the cache, but values aren't the most up-to-date values for that data structure. Not present means the data structure is not in that chiplet cell2 cache. Bear in mind, these are all anticipatory states because all transitions are also happening in an anticipated fashion based on the mode of access of the data structure at the beginning of the kernel. We are preemptively calculating the state of a data structure in chiplets cache at kernel launch. Obviously, the table maintains a conservative estimate to ensure correctness. So we discussed about address ranges for data structures. What are they and why are they needed? Imagine a GPU program which is highly parallel and is reading and writing from an array A. The kernel is running on all the 4 chiplets and each chiplet is working on quarter of the array. If we had no range-based tracking, CPLite won't have any guarantees that one chiplet will only access the part of A that it modified in a preceding kernel. In a succeeding kernel, thus, we need to conservatively generate acquires and releases in case we can't track what part of the array A a particular chiplet accessed. But if we have these address ranges and we know that the chiplet is going to only read from the range of A it wrote to, we can avoid having to write back or invalidate this A from any chiplet's cache. But how do we get the access mode and address ranges that we have discussed so far? The answer is software hints. So we leverage the fact that the AMD driver stack is open source to add 2 new APIs called HIP set access mode and HIP set access mode range. The information about access mode and address ranges for the data structure passed using these APIs is ultimately embedded in the kernel packet. Now let's look at an example of CPLite in action. Here we are accessing 2 data structures, data structure A and B, on chiplet 1 and 2. We are accessing chiplet A, array A in read mode and B in read write mode, which corresponds to the chiplet vector states as you would see in the green box. Now a kernel 2 comes around. It is still accessing array A in read, but now array B changes from read write to read. This means there is some dirty data which needs to be written back. What we observe, if you look at the two blue rectangles to the right, is only kernel 2 is being launched on now one of the chiplets, right? So only the chiplet which did not, uh, only the part of array B which the chiplet now running kernel 2 did not write needs to be written back. So we only need write back from chiplet 1. So that is what is being generated by CPLI, uh, as you can see in the yellow box near the bottom of the screen. So in our evolution methodology, we simulate using the GEM 5v2 1.1 infrastructure. We run on 2, 4, 6, and 7 chiplets to test the scalability of design. The system parameters are shown on the slide. The three configs we run are CPLI, the baseline system, and the state-of-the-art multi-coherence protocol in HMG. HMG is a directly based cache coherence protocol, which keeps tracks of all sharers. They keep L1 coherence as it is and focus on the L2 like us. We also run a plethora of workloads from Rodinia, HPC, graph analytics, and machine learning domains. CP, Allied, and HMG make some fundamentally different design choices which are important to understand the performance results we will see later. So as CP Lights wants to leverage the producer-consumer mechanism, it wants to potentially save on flushes between kernels. Hence opts for a write-back cache. HMG goes a different way, and because they're adding a directory to the hardware, they want to piggyback on a VI protocol and always write through data to memory. Next, from profiling, it can be seen that most applications show locality for remote data. Uh, so no locality for remote data. So CP Lights works in a write no allocate cache policy, whereas HMG is designed to cache remote traffic. CP Lite builds on the GPU Viper protocol implemented in GEM 5, which closely resembles what modern GPU designs also follow. HMG, however, opts for a simpler VI protocol at the behest of more write-through and invalidation traffic. This design choice has a particular implication on remote traffic, as you will see in the results. First up is normalized performance. As I alluded to earlier, we ran all these 4 configs on 2 chiplet, 4 chiplet, 6 chiplet, and 7 chiplets. This graph is ordered in such a way that the amount of reuse in these applications starts from most on the left to least on the right. CP Lite is able to capture the reuse from most apps with moderate to high interkernel reuse. And it outperforms both HMG and baseline by the numbers shown on the screen. Apps with little to no reuse suffer performance loss with HMG because they maintain sharers and they need additional remote traffic for those invalidations whenever there is a write. HMG also does badly for applications with little to no locality in remote traffic because they are caching remote traffic and taking away space from local traffic which might have better locality. HMG has higher remote traffic than CP Lite baseline because of block invalidations and less reuse in the remote traffic. Due to no data retention, baseline has relatively higher L2 to L3 traffic over HMG CP Lite. And CP Lite is better than HMG in reducing L2 to L3 traffic because of no write-through traffic needed to maintain a sharer list like HMG does. So GPU vendors move to chiplet-based architectures has created new performance trade-offs at implicit synchronization points. Ultimately, this results in bulk write-back and invalidations for chiplets L2 cache as they become private to a particular chiplet in this new architecture. Our key insight is to track and be able to predict what data will be housed in the chiplet's cache to be able to only send out write-back invalidations when necessary. The proposed solution, even after being a coarse-grained tracking mechanism, was able to outperform fine-grained solutions in HMG and the baseline. Modern GPU workloads will continue to scale and have different requirements as we move ahead. Not only does CPA Lite show better scalability and performance than existing solutions, it also is reprogrammable, making it adaptable to future application requirements. Lastly, I will be discussing an overall conclusion to this talk. Ultimately, broadening spectrum of GPU application has resulted in new challenges for global synchronization on GPUs. We have proposed holistic approach to make GPU global synchronization faster, energy efficient, advancing the state of art for global synchronization on GPUs. The three pieces of global synchronization we discussed in this talk were slow explicit sync using device scoped atomics, where the challenge was that atomics go all the way out to the LLC and are slow. Our solution was to have local atomic buffers alleviate the bottleneck arising from inefficient implementation of these device scoped atomics. Next, we looked at the challenge of having explicit sync using software synchronization primitives. These primitives do not scale well. Our solution was to use the GPU memory hierarchy and consistency model aware algorithms to increase the scalability of these primitives. Lastly, we saw that new chiplet-based designs hurt implicit sync at kernel boundaries, where the challenge is loss of interkernel locality from the L2 cache. Our proposal was to track producer-consumer dependencies to make interkernel reuse less expensive in multi-chiplets. So, what are the final takeaways? The core GPU principle of massive parallelism will continue to be the driver of their wide-scale use. Modern applications, however, do much more than just being parallel compute engines. They use global synchronization frequently, thus making it a critical component for app efficiency. As GPU vendors continue to scale power, synchronization cost is going to become an even bigger component. We propose hardware, software, and co-design solutions to improve the efficiency of global synchronizations to help continue the scaling of these applications on heterogeneous systems. Thank you.
Thank you, Preyesh, for the great talk. Very interesting. So now we are ready for questions. So anyone from the audience have any questions about it? So I saw one question from Marco. For the CP Elite, you mentioned remote access has low reuse, so you don't track it, right? And since it is reprogrammable, could it be updated to track remote access if that fact changes? Or how can it be reprogrammed?
So, remote accesses is actually something to do with the cache allocation policy, which I discussed here. So we did some profiling and saw what is the locality in remote accesses. So if you cache remote accesses, you're taking away space from local accesses, which the chiplet is doing, right? So in case you have low locality, right, you do not want to cache something which is not going to be reused much, right? So in that case, you uh, do what CP Lite does. But let's say in the future, applications come around where remote locality is high. Then there is some benefit. As you will see in this graph for RNNs, HMG is doing slightly better than CP Lite. Why? That is because RNNs have good remote locality. So then HMG shines because it caches the remote accesses. So in our profiling studies, it was very infrequent that remote accesses had locality, but in the future, if it changes, it's basically a matter of changing the allocation policy for CPLI.
Okay. So I actually have a similar question related to the remote access. So here, when you're talking about the remote access, is it about, let's say, it's remote regarding its whether it's for this chiplet or whether it's for another chiplet, right?
A remote access would be any access where basically you need data from another chiplet's L2 cache
Yes. So
or
that's
memory.
regarding
Yeah,
the chiplet level. Chiplet
yeah,
level.
yes, yeah, yes, yes.
So is it supported purely in hardware, let's say? It's a purely hardware detecting, okay, this is the remote access, or is it
Yes.
something that software can also?
Yes. So I didn't go into the detail, but it is done through a first touch page policy. So we designate home nodes. So let's say there are two people, or two processors, processor A and processor B. Processor A accesses one address first. It becomes the home node for that address. And processor B accesses address 2 first. Processor 2 becomes the home node for address 2. Now, if processor A decides, okay, I also want to access address 2, now access 2 is currently in processor 2's cache and is now remote access for processor 1. And if it access addresses 1, that is a local access because it is the home node of that address. So that is how the remote access is determined.
Okay, sounds good.
Yeah,
Then we
yeah.
have a few more questions from the chat. The first question from Delane is, did you work on the DLSS4 or multi-frame gen? If so, or if not, what are your thoughts on the future of the DLSS or multi-frame gen?
No, I did not work on DLSS 4. Um, uh, Could you actually, I'm not aware of the details of that frame. Dylan, if you could expand on the chat, maybe I can talk about it more. Maybe I just don't know the exact naming. I know the concept. So if you could expand in
Okay,
the chat, we can. Or you can ask me offline also. That's all. Yeah.
sounds good. Uh, yeah, then a follow-up question is, since it depends on command processor, so does the asynchronous kernel start, let's say the scheduling algorithm decided to start one GPU earlier than the other, so does the table pop up in the CPU line to handle this?
Yes. So basically what happens is when you launch a kernel, right? When you launch a kernel, you need to ensure that all cache maintenance operations, that is release and acquires, appropriate release and acquires, have been sent to the chiplets and the chiplets have completed them before the kernel can begin. Otherwise, you will compromise correctness. So there is this, like imagine like a handshaking protocol where the global command processor sends, okay, chiplet one release, send write back your L2 cache. The chiplet one says, okay, I have written back my L2 cache. And then once it knows that, okay, all of my demands have been met, then this global CP starts the kernel.
Okay,
Yeah.
cool. So we have another question. What is the challenges for the synchronization as the number of GPU scales? So will the optimizations in CPU Lite apply? This is for, I think this is for the chiplet level scaling.
So actually, as GPU scale, CPA Lite becomes even more important, right? So imagine you have multiple tasks happening on multiple kernels happening. Like if you guys are aware about streams, so you imagine multiple kernels happening on multiple GPUs, then we actually do not need to write back and invalidate data from different streams because they're just happening in an independent fashion, right? If we had no essence of what kernel is, what chiplet is housing what data, we would need to do this. So as we scale and we are able to parallelize more stuff, we need this information even more. So optimization and CPA Lite still apply. So as I showed in my graph, we scaled to 7 chiplets and the results for CPA Lite got better. which is expected. So yeah.
Okay. Yeah, on my side, I have a follow-up question. So the
Yeah.
question in the chat is talking about the scalability at the chiplet level. Then what about the streaming processors in one GPU is growing larger?
So this is within one GPU, it doesn't matter, right? It's like within one GPU, CPLite is looking at shared L2 caches. So if you have more compute per GPU, basically you will have more data, right? You would want to scale your memory hierarchy in correspondence with how you're scaling your compute. So let's say if you have more data, there are potential more savings to be had there, right? But CPLite is like a solution which is related to data movement. So if you want to have more compute on your chiplet, you can. That's that makes sense. Like it doesn't directly impact, but with more compute, you would want more uh, a bigger memory system. With bigger memory system requires more data movement. With more data movement, you'll get more savings with
Mhm.
CPLite. So that is how it works. So yeah,
Right. Right.
yeah,
Hello,
yeah.
this is a Professor Jun Wang, and I'm not doing research in the GPU area, but I heard in the traditional CPU area, there's always a similar these are cache coherence protocols, right? For example, people develop their lock-free data structures and like least free or weight free data structures, which is a non-blocking program. And that can significantly save the synchronization overhead. And another hardware approach is called the transactional memory, right? And which was very hot in like 10 years ago. And I know that CPU is very different from GPU. I mean, for your this case, especially have the chiplet. So can this transaction memory or the log-free data structure techniques are applied to GPU?
Yeah, so thanks for the question. So basically, you're right. Transactional memory has been used to reduce the synchronization overheads out there on the CPU side. But the process of working of CPUs and GPUs are very different. GPUs process data in large parallel blocks and then synchronization at the end of kernels, right? So let's say if you were able to um, have some section of the data which you want to work in a non-synchronized manner, that you can do, like a even like a very simple example of like a critical section, right? You bound something in a critical section, acquire a lock, do all of the changes where uh, then you don't need to worry about synchronization inside that critical section. But anytime you want to become consistent again with the rest of the GPU, which you will need to do across the duration of the program, you need a global synchronization, which again will is very expensive on how GPU coherence protocols are designed. They are mostly software-driven VI protocols. So that is why we need the kind of solutions we need for GPUs, and we were able to not transport the CPU style solutions directly over to GPUs.
I
Yeah,
see. So something like
yeah.
in the multi-processor machine, right? This like directory based. There's other like a catch coherence protocol already there, right? Implemented in the commercial products, but that maybe is too heavyweight for the GPU, right?
Correct, because most of the data is parallel processing, right? If you implement a directory-based coherence protocol, then that is limiting the parallelism which a GPU can otherwise generate, because then you would need to track, okay, what processor has what line and what state. You want to let the GPU run free for as long as it can, and then only synchronize when you need to. Is what I would say. Yeah,
Okay, good. Okay,
yeah, yeah,
thank you.
yeah.
Okay, great. So, any other questions before we end today's talk? Any more questions from the audience? If no, I think that's probably the end of today's talk. Let's thank Preyesh virtually. And yeah, thanks everybody for joining. So I will see you next time. Take care.
Yeah, thanks everyone. Thanks Dee for inviting me. I will send Dee my email ID, and if anybody has questions, they can send me and shoot me an email. Thank you.
Sure. Thank you.
Yeah,
Bye.
thank you. Bye.